Hello, my name is Professor Hartwig Künzel from the Fraunhofer Institute for Building Physics, IBP in Germany, and I would like to welcome you to this new video. In the fifth module of this lecture series on the lighthouse project that are currently being built, everything revolves around the RANCHI location and the special way in which the building is being constructed here. Specifically, we will look at the construction of three-dimensional modular prefabricated modules, the so-called magic pods, and examine and consider them from a building physics point perspective. This submodule will therefore deal with energy efficiency enhancement at the RANCHI site. Specifically, we will look at solar energy gains. But let's start from the beginning and review the basics of energy efficiency in buildings. This energy balance equation should already be familiar to you from the other modules. On the left-hand side are the so-called sources, which means all effects that lead to an increase in the thermal energy content in the building or in the flat. On the right-hand side are the sinks, which relate to energy being transported out of the building. In this specific term, however, we want to deal with the influence of the sun, which is described in the balance equation as solar energy gains, QS. So the higher the solar irradiation on the building, especially through the windows, the greater this value QS and the total sum will be. Accordingly, with insufficient ventilation or low heat transmission losses, the room can heat up and lead to overheating. However, we will now take a look at exactly how large this value QS becomes, which means on which factors it depends and how it is calculated. QS is described with the following equation, which represents the sum of all windows and has watt as its unit. The individual elements that must be multiplied for each window are AI, which means the respective window area in square meters. In addition, there is the G value of the window, which is unitless and in short describes the total transmission of energy through the window. This was also described in the previous module 5.2. Finally, the value of the solar irradiance, I, is multiplied with the unit watt per square meters. If this calculation is carried out for each window and added to the total sum, this then describes the QS value, which means the total solar irradiance. Let's go back to solar irradiance again. This value depends on the meteorological boundary conditions. If measurements are carried out at a location, for example, with a pyranometer, such diagrams can result. Depending on the location, the course of the sun, and thus the angle of incidence, differs and can be described as a resulting irradiation that hits the Earth's surface. Depending on the time, the position of the sun changes, and therefore the irradiation on the surface differs also. Moreover, the incident radiation changes with the orientation as depicted in this graph. The displayed global radiation is the total value of the radiation which means the sum of the direct radiation and the diffuse radiation. That's the theory. Now let's look at a practical example of how the calculation of the QS value works. As already said, for each window, you'll have to calculate the solar gain and sum them up together. As a result, you get the total gain of the flat. If you want to get the gain of the whole building, you sum up all windows of the whole building. In this case, you can see the exemplary flat in RANCHI has a total of 5 windows. The area of the windows are 2 square meters, twice 1.8 square meters, and twice 0.75 square meters. The orientation of the flat means that windows A1 to A3 are directed to the east and exposed to solar irradiation of 600 watts per square meter. Windows A4 to A5 are directed towards the south, which results in an I value of 650 watts per square meter. So let's put these two values into the equation. To solve the equation, the respective G values of the windows are still missing. Depending on the type of window selected, different G values must be considered, which also significantly influence the overall equation. Let's calculate the example fed with variant 1 of the G value, which means the single glazing of the windows. The resulting total irradiation QS for the flat is 3685 watt. Let's take variant 2 of the G value, which means the double glazed window with external shading. This reduces the QS value of the dwelling compared to variant 1 by a factor of about 7 to 520 watts. In variant 3, the shading, in variant 3 without shading, it results in a QS value of 3295 watt. We can see that the QS value depends on the type of window, but the decisive factor is whether or not shading is installed. Let's have a look at the impact of the thermal bridges and blinds on the thermal gains. As an example, we use 4 variations of the bath window. So at first we have the window without thermal bridges on the upper left corner. Then the same window with some shutters in front. As version 3, the window is calculated with thermal bridges but without shutters. And last but not least, we have a window with thermal bridges and a shutter in front. Let's see the results. The window without thermal bridges leads to a gain of 6,800 kilowatt hours. The second window with some shutters in front result in 5,300 kilowatt hours. The window with thermal bridges but without shutters is calculated to 7,000 kilowatt hours. And the window with thermal bridges and shutter has a gain of 5,500 kilowatt hours. Finally, let's summarize everything again in a few key statements. First, we have learned that the solar energy input depends on the size of the windows, the incident solar radiation, and the G value of the glazing. Furthermore, the solar irradiation into the building depends on the location of the building and its orientation, as well as the respective time of year and time of day. Finally, we found that the combination of double glazing with additional shading has the greatest effect on the solar energy yield and thus leads to the highest thermal insulation. And with that, I would like to close my presentation. Thank you very much for your attention, and until the next video, goodbye.